So first we prove lemma 1. So we are trying to prove all the lemmas which we used in the proof of the unique factorization of ideals in Dedekind domains. So the first lemma is that every ideal A in a Noetherian ring contains a product of non-zero prime ideals. So we will prove this by contradiction. We will say that there are some ideals which do not contain a product of non-zero prime ideals, and we will reach a contradiction. So we suppose that there are ideals that do not contain a product of non-zero prime ideals, and we want to reach a contradiction. So what we do is we construct a set of ideals which do not contain a non-zero prime ideal and choose a maximal element of this set. So you denote the maximal element by I. So I itself is not prime because it is element of this set, and there exists A and B in ring A such that AB belongs to I because I is not prime. So there have to be elements A and B which do not lie in I, but their product lies in I. So A and B do not lie in I because I is not prime since it belongs to this set here. So now you construct two ideals. So this is actually math frac of capital A. So this ideal A is ideal I plus this element A. So this strictly contains this ideal. And then you construct an ideal B which is ideal plus this element B. So these A and B, this also contains I. But if you find the product of A and B, so product of these ideals A and B, their product is contained within I because you have AB lies in I and then everything else has a product with I, so they will lie in I. But A and B are bigger than I. So if A and B are bigger than I, they do not lie in this set. So if they do not lie in this set which has maximal element I, so they must contain a product of prime ideals because they are strictly bigger than ideal I, because neither A nor B is contained in I, so they are bigger ideals. So they must contain a product of prime ideals. So if they contain a product of prime ideals, then the product of these ideals lies within I. So I will now contain some prime ideals which come from A and B, and that is a contradiction because we chose I to be the maximal element of a set which does not contain a product of non-zero prime ideals. So that contradiction proves our lemma 1. So now we prove lemma 2. So say we are given ideals A and B. These ideals are relatively prime, and we have to show A to the M and B to the N, where M and N are natural numbers. These two are relatively prime. So you pick an element A in ideal A, B in ideal B, such that A plus B is 1, and you can do that precisely because A and B are relatively prime. Now we write the binomial theorem. So A plus B to the K is equal to 1, and we expand it like this. So if you set K greater than M plus N, then you will get a bunch of terms here with A's in it, which the power of A would be some power, say J, where J would be greater than M. So those terms lie in AM. And the rest of the terms will have, say, B to the power of I, where I would be greater than N. So rest of the terms would have that. So you have starting terms which will lie in AM, and the ending terms which will lie in BN. So and either the terms would lie in A to the M or B to the N, and this is equal to 1. So we have been able to find two elements whose sum is 1. Therefore these two are relatively prime. So now we come to lemma 3, where we have to prove this. So you start with P, a maximal ideal, and maximal ideals are prime, so you can localize with respect to this P, and you get this local ring A localized with respect to P. So it has a maximal ideal which is PAP, which we denote by a Q. And we said we have an isomorphism like this: A modulo P to the M. This is iso to localized ring modulo Q to the M, where Q is precisely the this maximal ideal in our local ring. So first thing we'll show is injectivity. So what we are going to do is we are going to take some element here. So the 0 element here has to come from Q to the M, and we will show that this element here, if you take something which is 0 here, which is in Q to the M, it actually comes from P to the M. So inverse image of 0 elements are 0 elements here. So inverse image of 0 elements here are precisely the 0 elements. So non-zero elements are not getting mapped to 0, and inverse image of 0 elements are 0 elements, and that will prove the injectivity. So we have to show that QM when contracted back to A gives precisely P to the M. Now what is this Q to the M? So focus on this portion here. So Q to the M is nothing but this P, this prime ideal P extended in this ring, localized ring AP. So Q to the M is P, A, P, M, which you write as S inverse of PM, because you have fractions here. This is a local ring, you have fractions here, where S is just A, you take out all the elements belonging to the prime ideal. So this S is the multiplicatively closed set. So what does the element of this look like, which is exactly equal to this, which is equal to the Q to the M? So you're taking the 0 element here. What does it look like? So it is of the form B over S, where the numerator belongs to P to the M. So the 0 element here is of the form B over S. Numerator belongs to P to the M, and denominator belongs to this multiplicatively closed set S. So now we have to consider its contraction and say its contraction back here is to some element A here. So A is in ring A. So this comes from this element A here. So this A is equal to B over S, and that should, and SA is in P to the M. This implies SA is just 0 in A P to the M. So you have A equals to B over S. So SA is equal to B. B is in P to the M. So SA is in P to the M. So now we are here. So SA is in P to the M. So we have SA is just 0 in this ring. So what we want to show is that this A itself lies in P to the M. So this A itself is 0. So from SA equals to 0, we want to have A equals to 0, and that will be the end of the story, because this A is essentially the contraction here. So you take A here, or you extend A back here, you will have A equals to B to the S, and that's why you have SA equals to B to the P to the M. So that's how SA becomes 0. So we want to show that this SA equals to 0 actually implies A equals to 0. So we have to go from here to this implication sign here, and if this implication is true, then obviously this A is 0 in this ring. That means A is P to the M. So if you take B by S in Q to the M, you can find an element A in P to the M if we can show this implication holds. So that is our rest of the work. So first is that P is a maximal ideal. That's given to us. P is a maximal ideal, and therefore it is the only ideal which contains P to the M. So that is because if you work with a maximal ideal which contains some P to the M, where M is maximal, so M is maximal, therefore it is also prime, but if it contains some mth power, then it will also contain without any powers. So this is just by the definition of a maximal ideal. Maximal contains P to the M, then this maximal will contain P, and this implies that P is equal to M, because if M is maximal and P is also given to be maximal, if both of them are maximal elements and one is contained within the other, so there has to be the case of equality. So this is by maximality of P. So P is equal to M. So essentially what we have proven is that if P is a maximal ideal, it is the only ideal which contains P to the M. So thus P modulo P to the M is the only maximal ideal in this ring, A over P to the M, because P is a maximal ideal. As we said, it is the only ideal which contains P to the M. So the ideals in this ring contain P to the M. So ideals in this ring contain P to the M, and we have only one ideal containing P to the M, that is P. Well, this is a maximal ideal. So this is the maximal ideal. So now S we are taking from this multiplicatively closed set S, which is all the elements in the ring A except those lying in P. So if you put S to P to the M, this will not lie in P modulo P to the M. So this does not lie in here. So by the non-unit criteria, since it lies outside the only maximal ideal, it has to be a unit. So if it is a unit, then you can invert it, then you can cancel this out, multiply both sides by the inverse of S, and you can get A equals to 0, and that's what we wanted to show. So now we prove surjectivity. For surjectivity, we are going to take some element A over S, and we are going to say this element A over S actually comes from some element XA here. So this is what we are going to prove. So we are going to start with some A over S here. So this A over S, this is the ring which is we are considering, because we are just modulo outing the elements by q to the m, but this is the big ring we are considering. So it is ring of fractions. It is of the form A over S, where A lies in our big ring A and S lies in the multiplicatively closed set S, which is from A you take out all the elements P. So P is the maximal ideal. Now these two are relatively prime, and therefore S and P to the m are also relatively prime. So you immediately have this form xs plus y is equal to 1, where x belongs to A, y belongs to P to the m, and S belongs to the multiplicatively closed set S. So we are taking this now. So these two ideals are relatively prime to each other, precisely because this S lies outside the prime ideal P. So now you have xs, so this from this you get this statement. Now you modulo out with respect to P to the m. So if you modulo out with respect to P to the m, y lies in P to the m, so you will have xs is equal to 1 in A modulo P to the m. So in this ring, xs is equal to 1, and therefore you can set x is equal to S inverse. So once you set x equals to S inverse, and x you see here is in A, so S inverse you set as x, so it is coming from x times A, and that's what we wanted to show. You pick up any element A over S here, you can find you can write S inverse as x here, and this x precisely comes from this equation, which leads to this equation, and you can modulo with respect to Pm here, because you anyway in the end wanted to modulo with respect to Pm. To get this equation, you need just this S and P to the m to be relatively prime, which just comes from the fact that this this ideal generated by S and then this P, they are relatively prime.